All right, thanks for coming. I'm excited to introduce our speaker for today, Nick. He's a new employee at the USGS Watershed, but not new to the area. He's at Ogden and King's University for undergrad in history, but did some undergrad research in this department. And from there, he went to the University of Montana, working on modeling groundwater age. He was actually advised by one of Pitt's old students, Clayton Gardner. Today, though, we'll hear about some of his postdoc work at Berkeley Lab in California, thinking about how climate is altering groundwater storage and high elevation mountain water. So, yeah, thanks for coming, and particularly on short notice, filling in the gaps. So, looking forward to your talk.
Well, yeah, thanks, Sarah, and thanks all for coming. I'm really happy to be here. As Sarah mentioned, I was a chemistry undergrad, but I spent most of my time here up in the labs on the fourth floor, and that's really what sparked my interest in environmental science, eventually moving to hydrology. So it's really great to be back in this classroom and giving a talk. So what I'm going to be talking about is a application of using both environmental age tracers, so some geochemistry, couple that with some large-scale hydrologic modeling to try to better understand the role of groundwater in mountainous watersheds. So for some acknowledgements, of course, first and foremost, Erica Sorella-Woodburn at Lawrence Berkeley National Lab was my postdoc advisor. I'm very influential in all of this, as well as many others from Berkeley National Lab, Rosemary Carroll and Peyton Gardner at the University of Montana. And then, of course, a lot of this involves data collection, and at that data collection in high elevation mountain systems, which is not easy. I want to thank all those who've helped with the data collection and the field work. And I often joke that when I would show up and wanting to collect these environmental tracers, it's gonna like, oh gosh, we have to now haul up all these pumps and everything. And I'm sure people weren't excited to help me backpack things up the mountain, but I'm very grateful for all the help. So just a very quick overview of the talk. I want to provide some context and maybe some motivation on why we should better understand groundwater way up in mountain systems, and how can we use environmental tracers as well as estimates of groundwater age to really better understand groundwater flow and storage processes. Then finally, there's a application of a high performance integrated surface water groundwater numerical model that we can try to understand both experimentally with observations as well as predictions. What's the groundwater doing, and is it important? So mountain systems, especially here in the Western United States, are really important for our water resources. So in these types of systems, seasonal snowpack is really the main driver of the hydrologic cycle. So we accumulate snow, we melt it, and that snowpack is the main driver of surface flow. So what we see in the rivers, what goes into the groundwater system is recharge, eventually comes out, evapotranspiration from soils and trees. So the seasonal snowpack is very important, but some somewhat recent work from Erica Woodburn, shown in this figure, is seems that projections suggest the Western United States in particular is heading towards more what are called low to no snow futures. So years where our snowpack is very minimal. And what we really need to understand is the coupling between this driving force and a decline in this driving force and the rest of the fluxes through these mountainous watersheds, because they are so important for our water resources. However, this is, as I'm sure many of you know, very hard to identify the coupling between all this. These systems are very hard to access, let alone make observations in. So in response to a lot of these questions, Lawrence Berkeley National Lab, which is in California, stood up a large DOE-funded watershed observatory. So this is called the East River Watershed. It's near Crested Butte, high up in the Rocky Mountains in Colorado again. This is a large DOE-funded project. The East River Watershed and the overarching project is really interested in trying to better understand water fluxes and also solutes geochemistry that are coupled to these water fluxes, and really understand what's happening way up in the mountains where we are receiving this bulk of the snowpack. So a big task that they have performed and set up is installing a bunch of instrumentation here. So this is maybe one of the few watersheds, especially here out west, where there's a whole lot of information in terms of all the way to the atmosphere, through plant canopy, down into the groundwater system. And this system in particular, this East River watershed, is in the upper Colorado River Basin. It supports one of the main tributaries to the Gunnison River, eventually moving to the Colorado River, which, as we know, supports really millions of people downstream and has been experiencing pretty significant declines in the past decades. So this system is experiencing a lot of change, but understanding this change is incredibly important, especially here out west. And some of the questions I went into as a postdoc working on this large project is, how does groundwater actually responding to observed climate warming and drought disturbances that have been characterized in this system? And in particular, does potential for deeper groundwater storage, can this water stored underground buffer stream flow, especially during drought periods? So this is, I think, pretty basic questions to ask, but when you're moving into mountain systems, for instance, the Wasatch would be a great analog, it's quite hard to install groundwater wells. So making direct measurements of the groundwater is quite challenging. So these are just some images of typical terrain access in this system. While there are some dirt roads, the wells are not on dirt roads. They're hard to access. They're hard to maintain. So it really requires a lot of effort to collect this data. Nonetheless, Berkeley National Lab and the many great techs working there have collected data over the past 8 or so years. And what I'm showing here is the groundwater level observations from one of the wells in this watershed. The x-axis is day of water year, and each color is a different water year. Y-axis is groundwater level observed in one of these wells in meters above sea level. What we're seeing is that going from 2017 through 2023, there's quite a large and continual decrease in the groundwater level observed in this mountainous system. The groundwater levels have declined upwards of 2 meters. So we're actually observing this loss of groundwater. One of the main questions we want to understand is both why and what's the impact of this groundwater storage loss in the overall hydrologic processes, for instance, stream flow production. So out of this East River watershed, there's been a lot of great work. One of them, a recent one, thinking about groundwater, is from Rosemary Carroll, shown here. On this plot, this is a modeling study through time, so the past 30 years or so. On the y-axis is the groundwater storage anomaly. So positive values mean you're gaining groundwater storage, so putting more water in. Negative values mean you're losing groundwater storage. What I want to highlight is the past 6, 7, 8 years, these clear bars, which is the historical data. So what we think is happening in the system, we're losing quite a bit of groundwater storage in the system. And when you warm the air temperature within this modeling context by +4 degrees, which is shown in these orange bars, we lose a whole lot of groundwater storage in this system. And it's losing at a faster rate as well. So what are some of the implications of this storage loss? Again, in this modeling study, in this plot, x-axis is time, stream flow for characteristic water years, the y-axis. The black line is the historical, so what we think is happening now. We can warm the system in the model, we can reduce storage, and the overall outcomes of this, I think, are best described by the title of this manuscript, just shown here, which is Declining Groundwater Storage is Expected to Amplify Mountain Stream Flow Reductions in a Warmer World. So this reduced storage, we expect groundwater and surface water to go down together. Here's just another quote summarizing this, that mountain stream flow is threatened by irreversible simulated groundwater declines. So this study is really highlighting the importance of this coupling between groundwater storage loss and stream flow loss, which is ultimately what we're feeling downstream. So this is a modeling study that I just presented, and it's using just the physics to characterize the groundwater system. A lot of what I've done through my PhD and postdoc is try to understand the groundwater processes through the use of groundwater age. So another figure from Rosemary Carroll here on the right. Groundwater age, so this red flow path starts way up at the top of the hill slope, moves down. It's a very long flow path. It would be characterized as an older age compared to these more shallow and intermediate flow paths. And potentially how these groundwater ages are really useful is that they can begin to constrain both storage dynamics, processes in the groundwater systems. For instance, is the water table really shallow? Is it deeper? Are we producing more ephemeral versus perennial streams? So these age tracers provide us some observations that's integrating across a bunch of processes. An example from one of my recent works, here's again a numerical model of a hill slope where we have 5 different realizations of what this hill slope subsurface could look like. These are very uncertain properties. And when we solve this numerical model and simulate groundwater head, so an observation at a number of wells, for instance, all 5 of these models can equally fit the observed groundwater level head data. As we can see here, the age dynamics, which is shown in the color, they can vary quite widely. So this is suggesting, and this is well known, that measuring groundwater age can really put constraints on the hydrology and the subsurface configurations in a way that observations of water levels may not be able to. So you may be asking what groundwater age somewhat makes sense. The longer water's been in the subsurface, the older it is. Measuring it is another process. And here at the University of Utah, I'm sure Kip will, some of the world experts in this, and they've also been providing a lot of this data. So very grateful for that as well. The idea is here in the atmosphere, we know somewhat the dynamics of various isotopes, geochemical constituents. When water enters subsurface as groundwater recharge, these isotopes, geochemical tracers, are isolated from the atmosphere, and we can use properties of them, such as decay rates, how fast they accumulate from subsurface rock-water interactions. We can use these time-sensitive processes to characterize groundwater age. There's this whole list of tracers, they're called environmental tracers, which is shown here on the right, that can provide information. One of the key points is that each of these tracers can really constrain only a segment of what the age distribution could be. So we have a number of tracers that are good for water on the order of tens to hundreds of years. Some provide information on much older water. Some have even larger distributions. But my opinion is there's no perfect tracer out there. So measuring more, the better, to get more of this characteristic age distribution of the water. So this has been done for a long time. It's been applied with great success. I would argue in mountain systems, it becomes quite a bit harder to both sample these tracers as well as interpret them. So this largely is an issue of data scarcity, and that measuring direct groundwater systems in these wells is quite hard. But we have that characterized and set up in the East River watershed. Another big challenge we run into is that interpreting, especially gas phase tracers, is quite a non-unique process in mountain systems where there's covariant parameters, and I'll get into that. And lastly, what I alluded to is when you look at a groundwater sample, there's many flow paths contributing to that sample. So there's a lot of mixing going on. We don't know that mixing a priori. So one of the approaches we developed a couple of years ago now is we wanted to take the classic interpretation of these environmental tracers and estimate both groundwater recharge conditions as well as these age tracers, and do so in a way that really robustly characterizes uncertainties as the result of this being a high elevation mountain system, a steep topography. So we did this again in the East River watershed, and this first study occurred on one single hill slope in this East River watershed. So the hill slope is about 1 kilometer long, spans a couple hundred meters, and there are 3 observation wells somewhat along a transect. The observation wells are about 10 meters deep, which is within this fractured bedrock system in this hill slope. So it's pretty exciting that we're actually getting samples from groundwater directly. We're not necessarily trying to infer processes from stream samples. We sampled noble gases, tritium, SF6, CFCs. So these are all tracers we can use to try to characterize age. So to think more about how we use, in particular, noble gases to look at the recharge elevations and recharge processes, we make measurements of a number of noble gases here at the University of Utah again. So this is neon, argon, krypton, xenon. What we measure and sample, of course, in the field is a function of the temperature of when that water sample entered the groundwater system. So if this is our flow path, the temperature here, the elevation or the pressure, also what are known as excess air parameters. This is just a schematic of a very common low topography system. And in such systems, the recharge elevation is pretty well constrained because it's flat. So we can make a pretty strong assumption on what that recharge elevation or pressure is. And that makes this problem fairly well posed. As we move into a mountain system that shows a lot of topography, the recharge elevation is uncertain. We don't know if the flow path came from high elevations or low elevations. Maybe more important is recharge elevation and the temperature at that elevation, they co-vary with each other. So higher elevations, lower temperatures. We all know that. So this makes the problem more complex in that there are more unknown parameters that need to be estimated than we actually have an observation for. So the approach we took to try to solve this ill-posed problem was to turn towards Bayesian statistics and do a really robust uncertainty quantification, how all these parameters co-vary with each other. Just very simple, the basic idea in this is we have a prior distribution, a full distribution. This encompasses what we already know about how recharge elevation co-varies with air temperature, which is shown here in the data. So this is the lapse rate, how air temperature and elevation co-vary from data. We also have our noble gas data. This feeds into the problem as a likelihood, and the updated full error distribution, uncertainty distribution, called the posterior, is the combination of those. And some keys to this process that we think make it very valuable is that it introduces this recharge elevation lapse rate as an uncertain prior knowledge. So we're not specifying it directly. It can vary. And the other really nice thing about doing the full posterior, you get all likely combinations of the parameters we're after. So elevation, temperature, excess air parameters. This is done in a very rigorous way. For example, what I'm showing here in this plot, this is the output of the MC analysis, where we're looking at each of the parameters that were estimated, and this is the joint distribution between them. So how each of these estimated parameters co-vary. What we can see by looking at these covariant plots is that many of them, it's assimilating our prior knowledge on the parameters. So as we would expect, recharge temperature co-varies with the recharge elevation, which is a good thing. But maybe more important, we get some of these parameter combinations that make very nonlinear distributions, and these nonlinear distributions would cause issues numerically for classic least squared estimation of these. The Markov chain Monte Carlo approach can characterize those quite well. So this is a great thing that it can help us overcome. So what do we actually learn by doing this full process of applying some Bayesian statistics to noble gas observations in these wells? So here's some of the results from two of these wells where it's elevation, recharge elevation on the Y, recharge temperature on the X-axis. Really, what I want to focus on is this blue region, which is the estimated error distribution, or what we expect the recharge temperature elevation to be at both the mid-slope well on the left, toe slope well on the right. This lower dashed line is the elevation of the well. So if the recharge was right at the well, this top yellow line is the very top of the hill slope. Really, what caught our attention is that the mid-slope well, higher elevation well, has quite a bit higher recharge elevations, colder recharge temperatures compared to this toe slope well. So the blue region's at a higher elevation on the left compared to the right. This is somewhat counterintuitive if you think of a hill slope where there's what are called topographically driven flow, where these higher elevation wells are likely getting these shorter flow paths, and what's coming up lower on the hill slope would have higher recharge elevations. So the way we're interpreting the warmer recharge temperatures at the bottom of the hill slope at this moment is that there's more mixing going on here. So this well down here is likely a mixture of shallow flow paths plus deeper flow paths, and these shallow local flow paths are likely contributing warmer water. So to expand on this conceptual model and move from noble gases towards some of the age dating dynamics we're observing, here's again a conceptual model of our hill slope right now. And each of these lines are what we could imagine some flow paths contributing to a well where we sampled. So the idea is we have a younger component flow path system, which are these green lines. These are characterized by, of course, younger ages, and then mixing within that well is a deeper, older flow path system. This is the red line. This older component has its own separate age associated with it. And then, of course, the masses have to balance. So there's a fraction of the young, fraction of the old, which is related to it. So this is called a binary mixing model, where we're assuming there's mixing of young and old water in each of these wells. We use the tracers, tritium, SF6, CFC, helium, these age tracers that sensitive to age. We again applied a full Markov chain Monte Carlo uncertainty analysis to come up with what we expect or think the groundwater age at this well could be. So again, on this bottom plot, these are the uncertainty distributions from the MCMC approach. The top is the mid-slope well, the bottom is the toe slope well. Here on the left is the age of this young flow path system, so these green flow lines again. The ages we're coming up with are on the order of decades to maybe 100 years. The amount of that system that is the young part varies quite widely. This is a very uncertain parameter, but it could be 40 up to nearly 100%. And then what's surprising is that the age of the old system, the old flow paths contributing, can actually be many thousands of years according to the tracer analysis. So there's young water contributing, but also very old water making it into these wells. And I guess the last point is moving downslope, we see that the water is getting older, especially this contribution from the old groundwater flow path. So that's a very in-depth analysis of 2 wells and a handful of tracers at a single point in time. We've since been really throughout this watershed, which is shown here on the left, where we've sampled over 12 groundwater wells, and we have about 22 samples in total. The sampling depths in all these wells are generally in the bedrock aquifer. They range from about 5 to 40 meters below land surface. And I would argue in a mountain system, high elevations, difficult access, this is quite a large data set of these environmental tracers that we've been collecting. Here's just a very quick overview of both the tritium, observed tritium on the left y-axis, and what's called the helium R over RA value on the right y-axis. But what I want to highlight here is that these 22 samples are distributed over a number of months in different hydrologic regimes. So we have base flow samples from the winter, we have peak runoff samples from groundwater, and a midsummer and then late fall base flow samples. So there's potentially interesting temporal patterns we can learn from this. So very quickly, the way tritium works is we have this known concentration in the atmosphere that it's fairly constant, and it peaks in the 1950s and it goes down to zero concentration. You go back about 100 years. So this is tritium dead water. It's a very good marker for water that is fairly modern, so the past 100 years or so. This is the piston flow model. We can also assume some mixing patterns where there's exponentially more young water in the sample compared to tritium dead old water. And this is how the mixing line, or what you would expect tritium to look like through time, on this bottom axis. When we apply this exponential model assumption to all those samples that we have, this is the ensemble of modeled mean ages that we come up with. So the y-axis is the actual measurement of the tritium, x-axis is the potential mean age. You can see that it spans many orders of magnitude, but I want to highlight that there's really a lot of samples that come up with quite low tritium, suggesting that they're quite old. We can do a very similar analysis with helium R over RA. Very basically, helium R over RA is the helium-3 isotope to helium-4 isotope ratio in the sample, and you can normalize that to the atmosphere, which we know quite well. And what we can see here on the y-axis again is what we measure in the samples, or not what we measure in the sample, what we expect to be the helium R over RA as a function of age. Really what I want to highlight is young water produces helium R over RA near 1. There's a peak if you have water from about the 1950s, and then it starts to decay with time. And as you have helium R over RA that becomes less than 1, becomes quite old, so hundreds to thousands of year old water. These are the observed tritium versus helium R over RA in a full suite of samples where we have co-located measurements. And really what I want to emphasize is that all of these samples ranging from 5 to 40 meters have tritium. So there's some modern component making it into this groundwater system. So no samples are tritium dead, suggesting there's a modern component. A lot of the samples, especially the lower tritium samples, correspondingly have low to low-ish helium R over RA. So that's this blue region shown here. So this suggests that the old ages suggested by tritium, which are these colors, indeed have another tracer marker suggesting there is quite old water. So the general conceptual model is mixing of young modern water plus deeper older water, all making it within these wells in the bedrock system. To look at it a little bit further, we can look at the tritium helium R over RA covariance. And in these plots, this gray line showing here is what we'd expect the age, different ages of an exponential model to produce in both helium and tritium samples. So a sample of 1 year would have a lot of tritium and a helium R over RA of 1. You march down this gray line. These black numbers are the age of that model. The red points are what we actually observed in all of these wells. So we see that most of them do not follow this model. But again, it seems that this system is a mixture of a young component, old component, and we can capture that in this pretty simple plot, where again, the young component would be this gray line. And then if we start mixing in an old component that has a constant age of 10,000 years, we can assume, for instance, we start with a sample, it's 10 years, and we start adding in little and little amounts of old water, 10,000-year-old water, and you start to move along this blue mixing line, where these blue numbers suggest that 10,000-year-old water and 20% of the sample is that old. The rest of the sample, so 10 years and 80% of the sample. We can, of course, do that from any starting point on this gray line. Really what I want to highlight is that the samples seem to fall along these mixing lines quite well. There's a number of samples, namely up here, that seem to be dominated by young groundwater. But as you move down, there's a number of samples that really have a contribution, a large contribution from this old groundwater. And this, of course, agrees quite well with this real in-depth analysis that we did earlier with the full suite of tracers and a robust uncertainty analysis. So mixing of young groundwater plus old groundwater in these wells. Another pretty novel piece of information we recently got is 39 argon age dating. So this is a pretty new age tracer that is being done at Heidelberg University with collaborators Werner and Christoph West. This is a great tracer because it fills in an age gap where the ages are 100 to potentially 1,000 years old. This is a very new plot that Christoph shared with me, but at one of the wells where we have this observation, this again is a distribution where the x-axis is the estimated age, and they're again coming in right at around hundreds of years, so around 350 years here. So here's again another tracer in this whole suite of tracers that's suggesting that this quite old groundwater does probably exist in this bedrock system. And if we look at some of the temporal dynamics at a single toe slope well, so this is a toe slope well, so right near the river almost. On the right y-axis in the black curve is the water table depth at this well, so this continuous line. The left y-axis, position of all these points, is the observed tritium, and the helium R over RA is the color of each of these points. You can look at this as a scatter plot form where again, water table is on the left axis, concentration of each of these tracers is on the y-axis. What we're finding is that the seasonal dynamics of these tracers varies quite a lot. So the groundwater age at 10 meters depth is quite variable based on the season. What we're finding is that the mean ages are youngest when we're melting snow, which makes sense. We're actively recharging the system, flushing in young water. But as we move to base flow conditions, we're no longer melting snow. The recharge declines quite a bit. The age qualitatively increases by quite a lot, which is quite surprising. And this suggests that the bedrock system is not some static reservoir, but it's quite dynamic, even on seasonal timescales. So to wrap up this first part, what we're finding, and I'm quite excited about, is that as you go down even to 10 to 40 meters in a bedrock system, there is tritium suggesting that modern precipitation is making it down there. So often hydrologists, watershed, catchment hydrologists assume that the bedrock system, not much is happening down there, so we can truncate our conceptual model, our numerical models to shallow depths. But what this work is suggesting, that having these deeper flow paths could potentially be quite important. And really, what we want to do with a numerical model, and I'll transition into, is look at the question, does the old age groundwater that we're actually measuring, is this buffering stream flow, especially during drought conditions? So we generated a large numerical model of the East River watershed. This is the Parflow CLM, and it's an integrated hydrologic model, meaning it solves both surface water as well as groundwater flow dynamics. It also couples in land surface energy balance terms, for instance, solving for ET, evapotranspiration. This model, like many models, is highly parameterized. It takes in all sorts of parameters, elevation, land cover, soil, the groundwater lithology, but it produces fluxes that are really important to understand. But what it does not produce is an estimate of groundwater age. To get at that, there's a model called EcoSlim, which is a particle tracking model. This model is coupled to the hydrologic model. The idea here is particles, so you can think of these as little balls. They enter the surface when water goes into the surface. They'll move along with groundwater flow paths. They can leave the system as evapotranspiration, so plants or evaporation. They can also leave the system as discharge from groundwater into surface water. So this is providing us an estimate on groundwater age, so we can track how long each particle is in the system and where the flow paths are actually going in this watershed. This is just an image of our numerical model domain. So this is the East River watershed up here. This is an hourly forcing data set. And really the output I want to highlight are groundwater storage. We can look at how precipitation is entering either as rain or snow, and the spatial and temporal dynamics of groundwater age. So here's just some first outputs of this model. On this top plot, the y-axis is the annual precipitation through time on the x-axis. The dark bluish color is the amount of the precipitation as rain, and the light blue is snow. So this is very much a snow-dominated system. And on this bottom axis plot is the groundwater storage from the model. What we can see is the model, again, is predicting these quite large decreases in groundwater storage through time, which again agrees with some of the observations that have been made in these wells. Similar to the Rosemary Carroll et al. Paper, we increased the temperature of the numerical model both by 2.5 degrees Celsius and 4 degrees Celsius. Now on the top plot, we have the original rain fraction in the dark blue. How much of the precipitation, more of the precipitation comes in as rain versus snow is this yellow, and then again for 4 degrees, increase in rain. So what we're finding as you warm the system, not surprisingly, more of the precipitation is coming in as rain versus snow. We can also see as we warm the system, we're losing more groundwater storage, and it's happening at a faster rate. In this plot, we're looking at the spatial as well as temporal distribution on where we're actually losing groundwater storage in this system. So the y-axis is the elevation in this watershed, and then again through time on the x-axis. The coloring here is when it's green, the 2.5 degrees C scenario suggests that there's more groundwater storage at a given time in elevation. As you move into the pink, red colors, that means warming caused a decrease in groundwater storage. Really what we're finding is that the model's predicting we're losing the most groundwater storage at the highest elevations. So these pretty pronounced pink colors are occurring higher up in the watershed. So we're draining the upper regions of this mountainous watershed. Also highlight that there's some green regions here. This is because we're melting snow earlier when we warm the model compared to the base model. So moving on to the particle tracking and the age analysis, this is what the particle tracking looks like from plan view. So these are all the particles that exited the model, colored by a qualitative age now, and this is at a single time step. So we have over 5 million particles in this whole simulation. They exit, we know where they exit, when they exited, the age they exited with, and we can aggregate all these particles within the watershed. And when we do that, we have some estimate of the aggregated watershed response at the outlet of this watershed. If we turn this map view into a time series analysis, so we collect all of these maps at every hour within the model, and we look at the distribution of ages. So y-axis is the total Q, so the total amount of particles leaving the watershed, and we've color-coded it into different age bins. So the youngest age bin, these light blues, are the particles with ages 0 to 14 days. Moving up all the way to the brown at the bottom is the particles, the amount of particles that are characterized with over 10 years age. Really what we find here is that this system, the hydrologic outflow of this watershed, seems to be dominated by water that is at least over 1 year old. We do see quite a bit of young water, so less than 14 days, this blue, when we're actively melting snow. So that's the dominant hydrologic signature, fast-moving water when we actually melt snow. But even when we do that, we never get rid of this quite old water. So this greater than 10 years is not responding to these interannual variations. In precip, snowmelt, it's just a constant steady flow out of the system. So I'll move very quickly here. I think I'm running out of time. We also compared those time series outputs to observed stable isotopes at the watershed outlet. So this is propagating observations of oxygen 18 in rain, snow, through the numerical model with all these particles. I'll just move on here to this plot, which is showing all these points are the observed O18 in streamflow, so pretty long time series. The blue curve is the predicted values from the model. What we're gathering from this is that the model is doing at least fairly well capturing the temporal dynamics, the O18, so the timing of base flow, peak flow. We get some information on years where there's more or less rain contributions. For instance, base flow is higher here. The model is, of course, not perfect. It's not capturing how flashy the system is. And this recession from the high values to the low values happens quite fast in the model, which is not apparent within the observations. So the last real quick analysis I'll look at is turning that full distributed time series into annual percentages of total stream flow. So in this plot, the left or the y-axis is annual Q, the fraction of annual Q, and this is for overland flow. So how much water making it into the river as overland flow. So no groundwater component. So it'd be about 30% or so. The black line is the baseline, and then how we change it with warming the model. We can do that for 0 to 1 year fractions, 1 to 3, and greater than 3 year fractions. And what I want to highlight is that these young fractions, so overland flow, 0 to 1, there's no long-term spatial temporal patterns, and there's a lot of variability that's following how much precipitation there was in a given year. As we move to these older waters, 1 to 3 year and greater than 3 year, we see that this 1 to 3 year bin in particular, there's this long-term decline as we go through time. And as we warm the model, we're losing more of this water. And this is being counteracted by this oldest portion of water, greater than 3 years, where it's actually increasing with time. And as we warm the model, stream flow is becoming more dependent on this older water. So the conceptual model here is that we have this fairly constant source of old groundwater that's draining into the streamflow system. But this intermediate age water seems to be going down, and especially with drought conditions. And that's what's highlighted here. So in this watershed, water year 2018 was a very low snowpack water year. What we find is that this has the highest fraction of the old age water that's greater than 3 years. And that stream flow seems to be more dependent on groundwater storage compared to this young water overland flow and 0 to 1 year old water. This is really important because there's been research again that as we go into the future, low to no snow years will be more common. We can expect them to happen more often. So understanding the hydrologic ramifications of the groundwater as we go into years with less snowpack, we think is very important. So some just really quick key findings that we found through all this is that the groundwater from our sampling seems to be a mixture of both modern, so young water, plus quite old water. This is suggested by the tritium, and we're finding tritium even down to 40 meters in a bedrock aquifer, suggesting that precip is making it down that far. Numerical models show that the groundwater and stream flow declines are happening with warming. This is especially the case at the higher elevations. And as we move into potentially a drier future, potentially the groundwater storage that is older in age could support stream flow in some sense. So with that, I'm happy to take questions and thank you all for being here. Paul also had his hand up, but either way.
That was a fun talk. I was a little surprised that it didn't seem to be a response, wet or dry, similarly to warming.
Mm-hmm.
And I'm curious about the volume change measured in it, and ages, and the lack of parent response.
I think there is a response. Are you referring to these?
Yeah.
So they're definitely, if you hone into water year 2018, quite low, poor snowpack. Groundwater system definitely is responding as not as much recharge. This is bounded on the left and right. Water year 17 and 19 were pretty good snowpack years in this system. And we recover a lot of that storage that was lost in this low snow year. So I think there is a response to.
What's the depth of rather than
Oh,
what's the depth compared?
In terms of like millimeters?
Yeah.
I don't know the exact number.
So for sure,
Yeah, so long. Yeah.
Consistent with your age.
Mm-hmm. Yeah, I don't know the answer. We did not normalize in this paper to millimeters on watershed area. There's a lot of limitations in this model that I think making that comparison would be tricky. One of the big limitations is the total depth of the model, which is quite shallow, 50 meters here. I think to capture, at least a lot of our wells even are pushing 50 meters. So to eliminate boundary condition effects in the model, we'd have a much deeper model we have not done yet. Mm-hmm. Mm-hmm. Yes, we're also finding that this age dynamics could be explained by matrix diffusion. There's a lot of fracturing here. So we have a new paper that maybe suggests it's not a volume component contributing the old stuff, but maybe diffusion. So much more local system, which has big impacts on conceptual model of flow paths, hydrology, active storage volumes. Thank you though for the question.
I was thinking about
Yeah, on this plot. I think that's likely highlighting a limitation here that all the tracers we've measured are not sensitive to that really young piece of the residence time distribution. So they really start at 10 or so years. And tritium itself is quite uncertain. So I think the better interpretation here is not 10 years, but there's some modern component. Yeah, this is tritium along with helium. Yeah, so no gas phase tracers, CFCs, SF6. Those end up being quite difficult in this watershed due to production of SF6, degradation of CFCs, lots of geochemistry happening that makes challenging. Yeah, good.
Here you've got in the first part, you instance 10,000-year-old water. And second part, the old age off at 10 years and older.
Yeah.
You know? So how in that modeling, how will the water?
This
Did you ever see 10,000-year-old stuff?
no,
Or is
this
that a limit?
is the limit of the model. This is a very large model, requires high performance computing. We're talking days of runtime, especially when you do particle tracking. So to make the model deep enough to capture those age dynamics, in addition to have a simulation time long enough, I haven't quite convinced the national labs that we need this giant, massive chunk of computer time to know what the groundwater age of our model is. Something we'd love to do, and something that's probably more suited for a different code, such as ModFlow, which runtimes are much less. But I would love to do a direct comparison with actual well data, but the model is just a different scale. And also, when we look at the model, it's coarse. We'll have like 5 wells within one single grid cell. But yeah.
One other question. So you also showed us some isotope data.
Mm-hmm.
Do you have tritium time series?
We did not, unfortunately. We have a couple of measurements. Most of them were synoptic, so spatial distribution. Yeah, I know from some of the other tracers, we don't seem to see like an old component in stream flow. But I think it's very seasonal, so we're still working on that. And there's a mini Rudy over there now, so they may be looking for some other noble gases.